Maybe we should get a third century or something.
90s or like there is
My book is just it's more a notebook than
Also, yeah.
MSI, MESI, MYSI, MOESI, Dragon, but I think okay, MSI, Illinois, Berkeley, MSI. Oh, those are updated protocols.
So I was like, oh, okay.
So if you have heavy read-write sharing, there one particular processor is not going to write again and again and update this protocol. But it results in a lot of bandwidth usage. So what you really need is each cache block, so you're updating when the console. Okay. When the console you switch to the validated for
There's only even one
Okay, so we finished off last lecture with this, okay, talking about the SIMT stack. How do we handle control flow divergence in sort of a situation where we've got branches and arbitrary control flow and threads are going to go in each direction, and we sort of went through the hardware mechanism of having a stack and how that's a very natural mechanism for dealing with this. One thing that we didn't talk about that I do want you to think about is what happens on the backwards branch. Okay, so in this piece of control flow, there's when I say backwards branch, does everyone know what I mean? Where's the backwards branch here? Which two nodes does it connect?
G and A.
G and A. Okay. In a program, what would a backwards branch be? A loop. Okay, loops implement backwards branches because you're moving backwards in the code, and they repeatedly do a particular subsection of code. And you'll notice that G, it is a divergence point, right? So some threads could exit the loop while other threads continue to execute the loop. Okay. And the way that this works is you will essentially have of this is if you have multiple threads in a warp and then they are traversing the loop a different number of times, which is very common, right? If you think about something like graph processing, every thread is processing one node, and then every node is like you're going to all the neighbors, and there are different numbers of neighbors in each node. Then that means that if there's a loop in there that's going over all the nodes inside the graph processing algorithm, some threads are going to go 100 times, some threads are going to go 2 times. And what you're going to end up with is, in the beginning, it will be nicely converged as they do the first few iterations of the loop. And then as threads begin to exit the loop, it will get more and more diverged. And then you'll end up with just the threads that are actually traversing this backwards branch executing, and all of the other ones waiting for the rest of them to complete and exit the loop. Okay. Questions on that? Yep.
What would be the convergence point or like the post dominated process?
Right. So what do you think?
Things are going down and then we'll again come back to G.
Correct. What would be the reconvergence point? The instruction after G. That is the immediate post dominator, because regardless of whether I take the loop another time or I am done with the loop, the first point at which both of those paths will do the same instruction is the block immediately after G. Okay, so you would essentially have a reconvergence point at this split. You're going to get this split at G, and the reconvergence point is going to be, I haven't listed it here, but it's essentially the next node in the control flow graph after G. Okay, that says once everyone gets to this particular instruction, we're going to reconverge. Make sense? And the kind of nice thing about this mechanism is that it's fully recursive. It'll work on arbitrary control flow graphs. That's why you can write arbitrary CPU programs with function calls and arbitrary complexity, and it will all execute on the GPU. It'll compile down, and the SMT stack will handle all of your weird branches. But, you'll pay the trade-off in efficiency if they don't go the same way. Okay. Questions on this? I will probably ask you some question on a loop at some point. Yes.
So does the hardware ensure that if a thread exits a loop, does it have to ensure that the threads that are inside that are still in the loop complete before between them?
Yeah, because basically the other ones are going to have to wait outside the loop, and the ones inside the loop will continue to traverse. Because it's essentially, this weird little junction here is sort of like an if else. Right? If you unrolled the loop, so that's one way to think about this, is if I unrolled the loop, I wouldn't get the backwards branch. I would get an edge that goes to another copy of this same control flow graph, and then another edge that goes around all of it to the node on the bottom. Okay? And actually, that's the right way to think about loops. The control flow sort of moves in, because this is kind of like an if else. It's just that one branch of this is going back. I mean, it really is. It's a conditional branch, right? Which is the same as an if else, but one of the branches is going backwards in the code. So it's a little harder to wrap your head around, but the same principles apply. You're going to have to keep doing that backwards branch, because let's just look at one unroll, right? So you've got this thing. It looks like whatever. It's got this sort of arbitrary control flow. And then if I unroll it once, then I would have one path. This would normally be the backwards one. It'll go to conceptually like another copy of this same thing, right? And then the other one will go all the way around to this new node that's at the end of that second copy. That's what's happening. Make sense? Good question. Other questions on this? All right. Okay. All right. So this can cause a problem. And like I mentioned last class, this is usually implemented with push and pop instructions in the actual ISA itself. If you go look at the machine ISA, the very limited documentation that it has, there are these instructions that say push and pop, but it doesn't really say what they do. And what they do is basically modify entries inside that SMT stack. You can also do this with predication. Who knows what predication is? Generally, in a vector machine. Some folks. Okay, so let's say I didn't have this crazy SMT stack. And let's say I had a big, wide, vector processor, like a Cray processor that was, let's say it's 128 wide, 128 floats at once. And I think you guys learned this in 565, at least basic predication, when you talked about vectors, right? So it may be the case that sometimes you have an if condition inside a highly data parallel loop, and you want to put it on a vector unit. But vector processors don't have support for this crazy SMT stack thing. But what they do have support for is a predicate register, where, if you had this big, wide, vector add, you would, if maybe it's operating on, these are the two sources, and then this is the destination. And then you have this additional register called a predicate register that you give it, which will have 128 entries in it nominally. And it will be a 1 if this lane should perform this operation, and a 0 if this lane should not perform the operation. And then you can have other vector instructions that write into the predicate register to set the lanes, bitwise operations, to set the lanes appropriately based on whether you want to do the operation on this lane or not. And this is how you would normally vectorize code that has conditionals if you were doing something on an x86 machine, with SIMD extensions or something. You can't do branches on the vector units because it's not supported. But you can do this predication thing where you sort of compute the predicate in software and then pass this extra register to each of the vector instructions to effectively get the same thing as the active mask that we have in the SMT stack. Okay, and GPUs also support this. So if you have very simple control flow, it can reduce it can basically eliminate the branch, and then just it'll write out both sides of the if else condition, and then it will predicate the one half that goes down the if with just whatever's in the predicate register, and then will predicate the other half in the else with not the predicate register to do the other path. Okay, which is essentially the same thing that happens when you think about the way the SIMT stack traverses, but it's explicitly done with predication. Okay, so is that familiar to most people, or at least the people who knew about predication? Okay, so they also support this. Questions? All right, so compilers will do this with simple control flow, but generally you do need this sort of SIMT stack. All right, so this causes problems. In the early days of GPUs, this was sort of one of the big primary issues. People were just writing this arbitrary MIMD code, some of which really had good convergence and some of which didn't. And you end up with this problem where you have what we call reduced SIMD efficiency. So if you just sort of count up the number of instructions that you're executing in your program, and then you count up the number of active lanes across those instructions, you use the number of instructions as the denominator and the number of active lanes as the numerator, and then you can get a fraction that says like what percent, what is your SIMD efficiency? Okay, like am I at 100% active lanes, or am I at an average of 50% active lanes, or whatever? And this is really a property of the program and the width of your SIMT engine. Doesn't matter what your cache looks like, doesn't matter what the rest of your architecture looks like. Like the delays in between the instructions can vary based on your microarchitecture, but the SIMD efficiency of a program is sort of innate to the program, okay, innate to the control flow based on whatever your inputs are. Okay, so the sort of basic way that this works in a baseline case, let's say we have like a sort of simple GPU where we've got a 3-cycle latency before we can issue the next instruction in a particular warp. And so like we have alluded to before, the way we cover these latencies is not to go issue the next instruction if there's a dependency or we have to wait, it's to go issue an instruction from a different warp, okay? So in this case, we're issuing, A from warp 0, instruction A from warp 0, instruction A from warp 1, instruction A from warp 2, and inside each of these little boxes, I have the number that indicates the thread number that's associated with this particular warp. Okay, so the first warp has the first 4 threads, the next warp has the next 4, and so on. And so if I'm executing and I have enough warps, everything sort of looks good, right? Like I'm issuing something every cycle. The downside is that if I have this region here where I have reduced SIMD efficiency, my machine is not operating at the rate I would like it to. Now, the point of this paper, this dynamic warp formation paper, and about 100 other papers after it, the loose idea around what they were trying to do was, take a look at all of the warps in the system. Okay, so I know that in one particular warp, maybe some threads are going one way and some threads are going another, so I have to mask them off. But what if I considered all the warps that are on the core? And they're all executing the same code. So chances are, if 2 threads go down the if path in warp 0, probably 2 threads went down the if path in warp 2 or warp 3 or somewhere else. So could I take that work that was in those other warps that was going down the same path as the C instruction here, for example, and can I group them together and form new warps? That's the idea. So dynamically, so instead of just statically saying, the first 32 threads are in warp 0, the next 32 threads are in warp 1, etc., I'm going to start off that way, but then as things start to go off into the weeds, I'm going to group them together, and I'm going to try to find the threads that are going through the same control flow path. And if I do that efficiently, I can basically take this one region where I have, all of these different warps doing the C instruction, but obviously, only 50% of them are doing it. Only 50% of the threads are doing it here. Only 75% are doing it here, and only 50% of the warp or the threads are doing it here. So if I could sort of pack these things together, I could create 2 instructions instead of 3. So now my latency goes down, right? Because now I don't have to issue 3 instructions to capture all this work. And each of those instructions has a way higher SIMD efficiency, so it's making much better use of the hardware. So my average efficiency here would have been somewhere between 75 and 50, right? So like 60-something% in the baseline case. And if I group them together and pack them into just 2 instructions, I could get an 88% efficiency and save a cycle of issue. Questions? Does it make sense? That's a basic idea. Okay. And so there's a paper, it was sort of the first paper that tried to attack this problem in GPUs called dynamic warp formation, where they have this pretty complicated technique. I will post the paper in Piazza for you to go take a look, but the general idea is you sort of have to have these kind of synchronization points where you're waiting for the warps to show up to figure out if they can be pulled together, and then have this sort of complex camming table to figure out which warps are going in the same direction, and then a pool to reform new warps, and then spawn those new warps off to try to make everybody go in the same direction, like do some kind of maximal packing. Yeah.
Would that add additional overhead? Would it be easier just to lose the efficiency, the efficiency?
So the paper suggests no, that it's better to do this than to add their crazy hardware thing. In practice, nobody ever implemented this for a few reasons. There's also some additional constraints on this reordering. Let me see if this example shows it. So do you notice, what do you notice about the repacked warps? The threads and the repacked warps? Something is consistent about the threads and the repacked warps versus the original instructions that they executed. What's consistent? Yeah. Go ahead. Don't be sure. What's that?
Their positions.
Their positions. What do you mean by positions?
So, if a thread was, if thread A was thread 0 in one, it
Yeah.
has to be 0 in thread 0 in the.
Right. So 1 and 2 are conceptually in lanes 1 and 2 of the vector. When I repacked, I kept them in lanes 1 and 2 of the new warp. Why would I want to do that? Yeah. Thread ID. No, that's not the core reason. Yeah.
Wait, for registers?
Yeah, for registers. Remember, we don't have like a bunch of scalar registers that you can arbitrarily access from each lane. We have big wide vector registers. So if I'm reforming these warps, I need, remember my thread, my register state is thread private from a CUDA perspective. So that means that I can only access the vector registers in lane 1 if I was originally in lane 1. I can't access the registers in the other vector lanes. I could, but then I have to move them. I have to shuffle them in and out of some memory space. You know, I actually have a patent on this that basically does this. Like, actually, no, that patent got denied, but we had a patent application that did this, where you like take all the register state and like put it into the shared memory and then read it back into the registers to try to, you know, make a more efficient packing. So, you know, this is sort of true of all of these techniques that try to do this reformation. They have to make sure that the lanes remain consistent when they do the reformation, because fundamentally you're using vector register files and SIMD units. Okay. Questions on that? All right. So all of that sort of got proposed in this paper. It showed some nominal speedups on some branchy code, right? The branchier your code is, the better this looks for you. The hardware overhead is sort of, you know, a bit of a hand-wavy architecture approximation of what the hardware overhead is, as you'll find in many research papers. The complexity is also, you know, a little high for, you know, trying to like tokenize things and sort of pool things together. And ultimately it was sort of a neat idea that never got implemented. And it also had, you know, some pathologies. So one pathology that it created is that, you know, I hammer on you guys to make sure that your memory accesses are coalesced, right? That nearby threads are accessing nearby data. If I have this crazy programmer invisible mechanism that is like moving around what threads are grouped together, then all of that hard work I did to try to make sure they all access the same thing at the same time gets busted. Okay, so for example, if I have, you know, this memory access here where I'm accessing C and I'm just indexing by TID.x, this should be a nice coalesced access, right? Because every consecutive thread is accessing consecutive value in the C matrix, and then I'm adding some K constant, okay? If I didn't do this formation thing, everything would line up nicely, right? And then I would coalesce my accesses such that, you know, all of these memory accesses are lined up together on the same sort of, nominally cache line, right? There's spatial locality when we start adding caches to this system across each of these accesses. So then in one access to the cache, I can service all of these threads, okay? Then the same thing is true of the red ones, right? And the brown ones. It's just one cache access for each of these load instructions. This is what coalescing gets you, right? It takes a load instruction that is accessing fundamentally different addresses across each thread in the warp. But if all of those addresses can be condensed into just one address, then you only have to go to the cache once, okay? Which means you only have to check one tag. So your cache, your sort of throughput there is sort of optimal, and you're able to service all of these threads with just this one tag lookup. When I do dynamic warp formation, even if I'm fortunate enough to still hit in the cache, let's assume that everything is sort of in the memory at sort of the right space. If I look at what happens, like the total number of cache accesses here is 3. In dynamic warp formation, I now have 3 different cache lines that I'm accessing in one instruction, which means that I'm going to have to go to the cache and check 3 different tags if I've got a line size of some nominal width, which is typically what GPUs look like. So now I have 3 accesses for this first instruction to the cache, 3 accesses for the next instruction, and 3 accesses for the next. I end up with a total of 9 tag lookups. So now I have to either increase the bandwidth of my L1 cache by a factor of 3, and that's actually what they did in the paper. So in the paper, to sort of get around this problem, they increased the port number on their L1 cache to make it so that this problem went away. You can do this sometimes in papers to align issues. As long as you're honest about it, you're like, okay, we know this is a problem. Like, if you just ignore this problem, this work will solve this one subset of problems, but it doesn't solve this other one. And then you know what you do? You propose another paper that fixes the problem that you sort of introduced with the with the first thing. Okay. So then this is bad. And this dynamic warp formation technique will do this. It'll sort of swizzle things around and it really won't care about where things sit in terms of memory. And yes, even if the L1 cache absorbs the traffic, so you don't end up with off-chip traffic, you still have a huge amount of port complex if you only have a single ported L1, or even a 3-ported L1. But if you have a 3-ported L1, you're okay, because in this toy example, because you can serve 3 accesses in one cycle, but typically the L1s aren't that highly ported. Okay. Another thing that dynamic warp formation screws up is if the programmer has explicitly programmed their code knowing what the warp size is. So the CUDA programming guide says, don't worry about warps, right? Warps is a layer below what you're supposed to worry about. But if you're a Ninja programmer and you really want it to go fast, you do have to worry about warps sometimes. And some programs will have been written assuming that the warp has a particular size. Okay, so this is a concrete example of a piece of code. This is a ray tracing piece of code where there's a task queue. You're sort of pulling off tasks from the task queue, and it was written assuming that the warp width was 32. And in this code, if you don't have warps 0 through 31 and 32 through 64 together, then you actually will end up deadlocking the code because it sort of assumes that there's an implicit warp synchronization at the reconvergence points, right? So remember, reconvergence points are where warps are going to come back together. If you wrote your code assuming that the warps were going to come back together at a particular point, that means that this code in particular, you're not allowed to leak some threads of the warps beyond this point without all of the other threads of the warp being at that place. Okay. And if you do that, you'll actually end up with, a functional error in the program. Because, if you rearrange some threads to be in different warps, those warps may not wait for the other warps or the other threads that were in the original warp. And now all of a sudden your program is broken. Okay. So, dynamic warp formation just sort of willy-nilly repacked things and then didn't do anything to fix them when they hit reconvergence points. So it ends up actually breaking code that used to previously work. Okay. So there's a follow-on work to this that does something called thread block compaction. And the core idea here is that code generally has convergent and divergent phases. Think about your CUDA program. When it starts off, everything's happy because there are no branches yet. Everyone's together. It's kumbaya. And then diverge because maybe you hit, a loop that has different trip counts, or you hit arbitrary control flow where they go in different directions. And then after it's done with that divergence section, it reconverges again, right? This is one of the nice things that CUDA allows you to do. It allows you to use vector units, and in the parts where there is divergence, it handles it and it functionally still works. And then it brings them back together. So you gain the efficiencies of having, wide vector operations in the parts where it is convergent, right? So divergence is always bad, but in being able to handle divergence makes it much easier to program. And if it's the sort of regions of divergence are somewhat limited, then the program should still be a net win on a GPU versus a CPU, for example. Okay, and so this observation is that, there's these divergent regions, and then they come back together, and then there's convergent regions. And so the general idea is that a lot of the coalesced loads and stores actually occur in the coherent regions. When you're off in the branchy code, the loads that normally appear there in code tend to be more irregular in the first place because they're sort of doing different things, they're accessing different data structures, et cetera. And so most of the stuff where you care about this number of memory accesses because they were coalesced in the original program is actually occurring in convergent or coherent code anyway. And so then the idea of this follow-on work was to fix those pathologies in dynamic warp formation by keeping the static warp arrangement in the beginning, then creating pools of dynamic warps inside only the divergent code. And then when I got back to code that was coherent, repacking the warps in their original static formation again. So let them go off into the weeds when the thing is divergent, and then bring them back together to create the original static formation after we're out of the divergent region of the code. And the nice thing about this is your control flow graph tells you where you need to do this. Okay? What's one idea? Where do you think I might want to how would I identify where a convergent piece of code begins, generally?
You look at the post dominators.
The post dominators, right? Immediate post dominators, you're going to have some reconvergence there. Now, maybe it's not total reconvergence because maybe you've diverged earlier, but in general, every post dominator is going to attempt to form some type of reconvergence. Okay. So if I wanted to, create crazy warps when they diverge, and then wait until an immediate post dominator and reconverge and make the static warps again, what would I need to do? What do I need to do at that immediate post dominator? I have a bunch of warps executing in the system. To repack everything back to their original static position, I want to do it at the immediate post dominators. How will I do that? Yeah. You need some kind of synchronization. Okay. You need to wait for all the warps to get there. So that way you can get all those threads at the same position and then repack them. Okay. Now it turns out that the programming model already provides a pretty clean interface for this. Thread blocks. Okay. Every thread block naturally has some number of warps in it. And so the idea behind this thread block compaction work is to essentially synchronize the entire thread block at every reconvergence point, or at least all of the threads, all of the warps that went into this that split right at this particular divergence point. And then when they get to that reconvergence point, you can put them back together. So the basic idea is let them diverge, repack things, and then let them reset and put them back in their original static formation. We'll do this at the reconvergence PC. The sort of core idea here is to treat the entire thread block like a warp from an execution perspective. So I'm going to have, let's say, 8 warps in my thread block. I'm going to run them all. In the normal situation, right, I'm allowed to have one warp hit the branch and then it diverges and I keep scheduling from that warp and it keeps going deeper in the code. But if I want to do this thread block compaction thing, I'm going to synchronize the warps every time we see a branch across a thread block. So the conceptual idea is that you have a sync threads every time you encounter a branch. So you wait for all of the warps in the thread block to get there. And then you resolve the branch to figure out where they're all going. And then you repack them optimally across the thread block and then let them go off. And then when they reach the reconvergence point, you wait for the weird warps you created to come back together, and then you just let them go back in their original formation. Okay. And we're not going to swizzle lanes around. We're not going to do any of that weird stuff. So that way, you know that your register is still in the lane where you did your work, right? Even though you did it with a different grouping of threads, it still all works out. Okay. And if I do it this way, I actually fix this implicit warp synchronization problem that I had with the dynamic warp formation, because now I'm synchronizing the whole thread block at all the reconvergence points. So that means all of the warps are also going to be synchronized at every reconvergence point. So that thing goes away. And all these uncoalesced memory accesses, because now when you get to those nice convergent loads, the warps are back in their original static formation. Okay. Questions on this? So this is sort of a more tractable way to do to handle divergence dynamically, at least control flow divergence dynamically. Yeah, question.
If some of those paths take too long
Yeah.
to reach the
Yeah.
synchronization point, then do you actually get any benefit?
So you can look. So like all good works of engineering, it's a trade-off. If you overpay for the synchronization, this could be slower, right? If you because you're intentionally slowing them down at every reconvergence point, and especially if you have, yeah, it really just depends on sort of the relative paths of each of the warps through the code. So if they get, every time you introduce new synchronization, there's a potential to increase latency. If you have enough warps, hopefully you can cover the latency so that something's still active, and that tends to be true, but you're right. It's a pathology that could happen. Other questions? Yeah.
So in the first work, we
Yeah.
were always doing that schedule,
Yeah.
irrespective of whether or not there was a factor.
So in the beginning, you started off with a static schedule because why not? And then every time you encountered any split, you went into the dynamic schedule pool and then it just opportunistically tried to put things together. Good question. Other questions? Okay. So what does this look like? So here's a sort of a cartoon of what I just described. So I've got these three warps. They're all doing instruction A. And so conceptually now we actually have a thread block wide SIMT stack, right? Instead of having an individual SIMT stack for every warp, I'm now creating this sort of thread block wide SIMT stack because I'm going to rearrange things as we sort of diverge among all of the threads in the whole block. So you get these three instructions executing. They're doing this sort of this crazy piece of code. Well, it's not really crazy. This very simple piece of code here where they do A first, and then they get to B, which is a conditional. Some of them are going to go down into C, and some of them are going to go down into D based on their thread ID or based on the value of K, right, which is some data dependent value. So the way that this mechanism works is that it basically does the same thing as the SIMT stack, except across the entire block instead of across the entire warp. So at this first point of divergence, you'll have two paths, right? Some of them will go down D, so that's this one, and then some of them will go down C, so that's this one. And then you'll resolve who is going which way. Okay, so you'll sort of see that, you know, in their natural state, some of them, like this first warp was kind of highly diverged. The second warp has some divergence, and then the first warp is 50% diverged again. So a similar pattern to the previous example. And then what I'm going to do is I'm going to do the packing, right, based on who's going which. You know, I have to take a look across the lanes, right? So this is just a greedy algorithm. If you sort of try to map this to the thing on the left, the thing on the right. So we start off and we have, okay, thread 1 and 2 are going to C, and then there's nothing in lane 3. So what's the first thing in lane 3 that's going down the C path? Oh, that's going to be 7. Okay, so I shove 7 in there, and then I look for lane 4. There's nothing in the first warp that's in lane 4. I look at the second warp, 8 is in lane 4. So then I put those together and I execute them like this. And then I do the same thing for the for the leftovers, right? Because I have more than 4 threads going down the C path. So then I pack the leftovers and I get this sort of reduction in number of cycles. After I finish that C path, I pop it off, right? I reconverge. Those threads have reached the reconvergence point of E. So they're done. So now I have to go do the other side of the path, and I go do the D path, and I do a similar analysis. So what is the first thread that's in lane 1? 9. Okay, the first thread that's in lane 1 is going to be 9. Okay, so that's going to be the first thread in the new warps that I create. So I have 9, 6, 3, 4. Right, because 6 is the first one in lane 2, and then 3 and 4 are the first ones in the other lanes, and then there's 10 left over. And sometimes, you can't get perfect packing, right? Like it'll never just work out. That it sometimes can, but not always, right? That they'll have like perfect. You'd be able to sort of resolve things perfectly to get rid of all divergence. So you'll end up with these sort of holes, and so you execute that one with less efficiency, but you had to do it that way. And then you finish and you pop that off, and now we're back at the top of the stack, and the thread ordering is the same way it was in the beginning. And I can go ahead and I can do that very last instruction with the same static thread ordering that I would have had if I didn't do any reformation in the diverged piece. And now that access to C is nice, instead of being a big nasty access that needs a hugely multi-ported L1 cache. Okay, that's the idea. Questions? Yeah.
So instead of using the greedy algorithm,
Yeah.
if there was some algorithm where you could schedule, like for example, in C 1 to 11, 12, and then the next is 5, 7, 8. So you have only 3 cache accesses instead of 4 in this particular group.
Yeah, so there's actually different algorithms that you could. So if, for example, you were, pardon me, if there was a load inside the C path, for example, that's a good observation. So if I actually was loading something, like this is just assigning a constant, so it's not really touching the memory system. But if inside C there was a load, that would have been nicely converged. I would want to try to minimize my swizzling, right? To minimize the number of memory accesses. And I think they evaluated different heuristics for doing the packing. Generally, the more complex you make that packing heuristic, more complex the hardware is, and you need to have enough win for it to be justified. And I think in most codes, so this is like everything in architecture, like what does the real program do, right? And it turns out that when you sort of diverge, usually inside control flow, usually your memory accesses also diverge if you're touching memory anyway. So it doesn't really benefit you that much to have things together. But you're right, if there was this convergence inside the diverged code, you would want to optimize for the least number of memory accesses. That's a good observation. And you could do that. It's just based on your packing algorithm. Other questions? Okay. Right. And so if I did this the normal way, right, if I did it without the thread block compaction, it would look like this. There's been, I don't know, recent is maybe a strong word. There's been a bunch of work on ways to handle control flow divergence by both GPU companies and researchers. That if you're interested in this topic, it's kind of mined out at this point. It's a little bit like branch prediction in CPUs. Like, yeah, it's still a problem, but nobody does papers on it anymore because it's largely solved, or at least it's either solved or nobody cares about it enough to solve it, is sort of where this falls. So there's, a paper from early micros looking at trying to reconverge earlier. So maybe you could reconverge before the immediate post dominator, for example, and you may end up getting better efficiency that way. There's another one for big warps. So this paper from UT Austin and NVIDIA was sort of, it's almost the same as thread block compaction. The idea is very similar, right? It's that you have a big warp instead of having, a warp across a thread block. And then they do this sort of repacking across this wider scope, very similar. There's been papers that have looked at simultaneous branch and warp interleaving. So what that means is that you could sort of do both paths, right? So instead of just having one path on the top of the stack, you could potentially do both and potentially have more than one instruction that executes in the SIMD. Temporal SIMD is, trying to, execute. It's sort of like that Intel thing where you're executing across a smaller SIMD width and then just doing it temporally instead of spatially. dual path execution. So you go down both the if and the else, but now you have to change your SIMD unit to handle 2 opcodes. And then I actually did some work at NVIDIA in mid-knots that looked at variable size warps, meaning that don't fix your warp size, have it be more flexible. The downside of that is that you have to build a machine that could handle the smallest warp size, right? And then, so you pay the cost of having, for example, a warp size of 4, but then if you don't need a warp size of 4, you don't pay the energy costs of like running 4 different front ends. You only want one front end if you're converged, and then you let them sort of split off. So you gang them all together. So we called it ganging, right? You'd like take all the warps and fuse them together to make a gang that goes together, and then the gang would split up, right? If they went in different paths, and then they could reconverge. And so it's sort of like a hierarchy. You can think of it like a hierarchical warp, sort of. And yeah, the product team, yeah, they never actually implemented it. There was a lot of talk at that time in NVIDIA about like small warps, right? Like I said, this was pre-machine learning. Okay, they weren't really sure what they were going to sell for other than graphics at this point. It's like they're like, oh, little warps, so then we can do like graph processing or like, you know, more flexible codes. And then it turned out that, well, no, people just want wide things because they just want to do gems. You know, the little stuff didn't matter as much, but it's kind of a neat idea. So anyway, there's a lot of stuff that sort of studied this phenomenon, and control flow emergence is something that, you know, is in GPUs. It lives in GPUs today, and you sort of have to know about it to understand how they work. Any questions on that whole line of work? I don't want to belabor it anymore. If you're interested, you can take a look at some of these papers that I pointed you to here. Okay. Yes.
I have a small question about the early reconvergence.
Yeah.
How would that go?
So you can get weird control flow graphs. Like, for example, so I have no pens. Yeah, which one? So for example, if I have, like, let's say I've got a control flow graph that looks like this. And then I sort of split off and like, this is split it off and like go, you know, in whatever direction. Like I have some arbitrary complex thing, and then I kind of come back down here. What kind of code might look like this? Where you sort of do the whole program in one side, and then you skip the whole program in another. What might that look like in software?
With recursion.
Recursion, no. What might I be doing to decide whether I should do the whole program or not? Validity checks, error checking. Okay, having some conditional that checks, you know, that checks for whatever, right? Like having conditionals that check to see if this is even valid to go into or whatever, and then the whole program goes down the other way. And that will create an immediate post dominator for the split point here, right? Because it pulls it out based on what the worst case is. Mm-hmm. Now, there may be points inside here where it's, you know, you're better to reconverge early, not sort of wait for this point where they're sort of going around. So that's kind of the general, it's more nuanced than that. I would encourage you to read the paper if you're really interested, but that's, you can end up with these weird control flow graphs that put reconvergence points at places that you don't actually have to wait for to reconverge. And you could potentially do it earlier. Okay. Other questions? All right. Another thing that is a problem with trying to run arbitrary MIMD programs, because remember, your CUDA program really is like a MIMD program. You've written it like each thread can make independent progress. Now, there's the SIMT stack thing that screws up your efficiency, but it turns out you can actually screw up functionality. So that implicit warp synchronization is one example of that. Like the programmer wrote the thing assuming that all the warps would be together when it executed the code. It turns out that you can write things like atomics that will break with if you use the SIMT stack. Okay, so what's happening in this little piece of code? So let's think about this from a CPU perspective. Okay, so I've got this mutex, and then I've got this while loop, this infinite loop that's trying to do a compare and swap with the mutex to basically grab the lock. Okay. And then once it grabs the lock, it goes inside the critical section, where really only one warp is supposed to be, and then it does the exchange of the mutex with 0 to turn it off, okay? If I look at the control flow graph that gets generated from this crazy thing, so A is here, it comes in, A is fine, everyone does the mutex operation. And then I go into this while loop, which creates this B block, which has a branch back to itself, right? Because this is what a spin lock or a spin loop looks like. Excuse me. And outside of the spin loop, I've got C, which is really the reconvergence point of where the backward branch goes, right? So what will happen in this code is you'll hit the atomic compare and swap, and this is on a per thread basis. So let's say the mutex starts out as 0, and I hit this atomic CAS on that mutex. What should happen?
One thread.
Only one thread should get mutex. Okay, not one warp, thread. So now one thread will grab that mutex, and then when it grabs the mutex, where does it want to go?
Critical section.
It wants to go here to the critical section in C. Okay, the critical section is whatever. Like, let's say it does the arbitrary code, and then after it's done the critical section, it'll turn off the mutex because it's done. It does the atomic exchange, turn it off. But based on what you know about loops and the SMT stack, what's going to happen when one thread wants to exit the loop and 31 of them want to keep doing the loop? You're gonna wait. No, not gonna wait. Yeah.
All of them. It's going for your hands to get threads that are loop instead.
It's gonna try and prioritize the threads going on that backward edge instead, which means that because it wants to reconverge, right, when they get to the bottom, it assumes that they're going to be able to eventually reach this reconvergence point. But the code is structured such that they never will, right? Because as soon as one thread in your warp grabs the mutex, it gets to the reconvergence point, and then it gets kicked in the shins and says, you have to wait. And it can't do the critical section, which means it can't release the lock. And then everyone else, all of the other 31 threads are going to be like, oh, I didn't get the lock. Let me try again. Oh, I didn't get the lock. Let me try again. And they will do this forever. And you'll essentially introduce it's live lock, really, because you're still spinning. You're still executing instructions, but you will make 0 forward progress. And if you wrote this in a CPU, you'd expect this to work, right? You'd expect it to, one thread would get the thing. And the reason is that you expect implicitly, whether you realize it or not, you actually expect a fair schedule in a CPU for among the threads that are operating and doing parallel code. But in GPUs, if you're using the stack, there's actually a very unfair schedule, and it will completely not schedule some paths based on others, based on the implementation of this sort of SIMT reconvergence business. So in the early days of CUDA, and this was like, they never really advertised this. People just started using CUDA and they were like, hey, I'm trying to write a lock and like it just deadlocks. What's going on here? And so actually this paper, there was a paper that people did to try to fix this problem. Was the impetus was it was like an NVIDIA developer blog post of like somebody trying to write a lock on a GPU and being like, it doesn't work and I don't know why. And then the NVIDIA people coming back and saying, oh, it doesn't work because you can't do this. And then they're like, wait a minute, you told me it was a MIMD programming model. They're like, yeah, but it's not really. So this is a problem, right? And in all GPUs before the Volta, this code would not work. Now you can restructure this. If you're clever, you can change the control flow graph. You can write a nasty looking lock and force the control flow graph to not look like this to allow you to get to the critical section. So the compiler could perform this transformation. It never did. So if you wanted to do locks before Volta in GPUs, you had to basically write your own nasty thing and then force it to write your own nasty thing with a bunch of macros to try to force the compiler to arrange the control flow graph not like this, so that way it wouldn't deadlock. Okay. Does everyone understand the problem here? Okay. So this is sort of like, introduced by the fact that we've got a MIMD programming model and we're trying to run that on this SIMT piece of hardware. And they sort of fixed this, and they fixed it by enabling threads that aren't just at the top of the stack to make progress. So the way GPUs used to work before the Volta architecture, which is like circa 2007, is the way I taught you, right? Where you would go down one control flow path, like you would A and B, and you could not do anything from X and Y while you were doing A and B because it was the top of the stack. But, and this is not a performance optimization. Okay, this is actually just a functionality optimization that they added. So then they increased the flexibility of the core itself such that you could do some of the path up here. Okay, you could do the A instruction and you could do the X instruction before you actually went to the B and reconverged. And then they added explicit warp synchronization instructions to get them to reconverge. Because if you give them the freedom, right, to go off wherever they want to go, then if you don't force them to come back together, they are going to just go off and do whatever they want. And so they made the warp synchronization more explicit in the ISA, so that way you could allow them to diverge and then have an equal priority on scheduling in different paths. And then when you wanted them to come back together, there would be this warp synchronization instruction. Now, none of you wrote any warp synchronization instructions in the code you wrote for this class, but you all ran it on a Volta GPU. I think that's what you've got in the cluster. So the compiler is doing this for you. So what will happen is the compiler will insert these warp sync instructions at every post dominator. And then if you're a clever programmer and you're like, wait a minute, I'm trying to do a lock, you can tell it to not do that in this region of code and then insert your own warp synchronization instructions. So the net effect of this was to give programmers the flexibility to sync their warps when they want, instead of forcing them to be sunk at reconvergence points. In the common case, right, in architecture, we always say make the common case work, make the common case fast. You do just want them to reconverge at the immediate post dominator. That's always the best thing to do. So that the compiler will just do this for you. But if you wanted to write your own log, right, if you wanted to write a critical section with a spin loop, you can do it because you can actually, force it to not put that warp synchronization instruction in, and then you can put your own warp syncs in where it's appropriate. Okay. Questions on this? And, some people, when they see this optimization, think that it's a performance optimization. It's actually not. Like, it doesn't get any faster to allow you to go from both sides of the warp. It just allows you to have the scheduling flexibility to not hang yourself on these implicit warp synchronizations. And you can inline PTX to do this, right? You can have an inline assembly instruction that will shove the warp synchronization instruction in there. Questions on this? So conceptually, this really means there's like a PC per lane now, right? Every thread needs its own program counter. Every thread could potentially go off in any direction at once, because you're allowing this sort of full flexibility, and they sort of pay the cost so that way you can get a MIMD ISA or MIMD like behavior. That's not what this paper proposed. So I mentioned that there was an academic paper. So this academic paper came out, and then like a month later, NVIDIA was like, "Oh no, this isn't a problem anymore. We just we introduced in thread independent scheduling to get rid of this problem." This paper has these big CAM tables to try to solve this in hardware. So an example of a paper that found a reasonable problem and a reasonable solution, and then the solution from industry was to just add more area and fix it in a sort of simple way. Questions on this? All right. Yeah, go ahead.
If you're writing code that has locks on GPU, would you just be better off writing it on a CPU?
Not necessarily, right? Because all code that isn't super data parallel and very, very with a huge amount of parallelism is not naturally a fit for the GPU. The GPU wants gems. The GPU wants dense computational operations. So does the CPU in some ways, right? Then it can use the vector units. It doesn't blow the cache, but real programs don't always have the behavior that you want for the particular machine. So there's always some spectrum of like, okay, if I wanted a lock, if I only need the lock once a millisecond, and then I can keep everything resident on the GPU, and I've got all this beefy computation I want to do, then it's probably better than trying to put it on the CPU. Now, if I have a program that wants to lock and unlock from every thread across all the GPU, every 24 cycles, then yeah, that's going to suck. So you're probably going to want to restructure the algorithm to not do global locking like that, or move it to the CPU. So there's this spectrum of like what would run best on what processor. And there's all kinds of workloads that will never hit peak performance on a GPU or a CPU. They're just memory bound, they're branchy, they've got like nasty memory accesses, predictions are wrong often. Those are the tough workloads to accelerate. GPUs have gotten in this sort of reputation for accelerating the easy ones, right? Like picking off the easy wins. But there is a spectrum of like, am I better off doing this on an accelerator versus on a more general purpose CPU? Okay, good question. Other questions? All right, these questions I think I sort of answered as we went through that code. Okay, that's it for the sort of first bit on the sort of basic pipeline, and then branch divergence. So like I said, lots of papers have explored branch divergence mitigation techniques in GPUs. Now let's look at the pipeline a little bit more. So the first pipeline that I showed you was what we call the one loop or one scheduler approximation, where you just had one fetch scheduler, right? And you were fetching, only ever one instruction from each warp was in flight at a time. That's not how real GPUs work. Okay, they actually have a decoupled pipeline, which will involve two schedulers. So this is more like how contemporary GPUs look. Okay, so you've got this SIMT front end. So that's sort of similar to the SIMT front end I showed you before. You're doing a fetch. Okay, so this is the fetch unit that's deciding what warp I should fetch from. You have the PC for that warp. It goes to an iCache decode stage. And then after it's decoded, it dumps the decoded instruction into what we call anyway an iBuffer. Modern GPUs have an L0 iCache, which is pretty much the same thing as this iBuffer, basically a place to store decoded instructions. And then the front end sort of keeps running. The front end can kind of run independent. The front end is sort of done once the instruction's been dumped in the iBuffer. So every warp, you'll sort of go to warp 0, you'll fetch decode its instruction, dump it in the iBuffer, then you'll go to warp 1, you'll fetch decode its instruction, dump it in warp 1's iBuffer. And so I'll have like a bunch of iBuffers or a bunch of space in the L0 cache nominally that holds the instructions that you may want to execute from every warp. Okay, so you have some buffer here. I stands for instruction buffer. But you can't necessarily issue those instructions yet, right? On an out-of-order CPU, what is this iBuffer starting to look like? What structure on out-of-order CPU is this sort of looking like? Sorry, reorder buffer I heard, sort of, you're issuing from it, so what's it more like? The issue queue, right? You've got a queue of instructions that have been fetched and decoded, and then they're living in this instruction queue because I need to figure out if I can actually issue them. And how do you figure out if you can issue them? How do you know if you can issue an instruction or not once it's been decoded? Dependencies, right? You have to pick up dependencies. I'm going to put this in the pipeline. It needs to read these registers. Are these registers written yet? So raw dependencies. Also other hazards that you might have. Read after write, write after write, write after read and write after write. There are potential hazards you can have in a pipeline. You have to resolve those as well. Turns out we don't have, there's one of these we don't care about. And we'll talk about that as we get deeper. But it's basically a place for you to look at all of the registers, to know what each instruction is reading and writing, and then pick out the dependencies to figure out if I can actually issue this instruction or not. And remember, at the register level, there's no inter-warp dependencies. I don't care what warp 1 is doing. I just care what warp 0 has done. So you have this extra flexibility versus a traditional CPU scheduler because you've got instructions in this iBuffer that are guaranteed to be independent, right? I've got 32 different warps or 64 different warps on this core. If I've fetched and decoded instructions from all 64 of them, then I know that there's no cross dependency between the warps. So I don't have to worry about that. I only have to worry about intra-warp dependency in my registers. So it gives you a lot of independent work to issue between. So then you have this I buffer, you have a scoreboard. Now this is not, do they still teach scoreboard in 565?
Yeah.
Okay, I thought we got rid of that because nobody uses it. But anyway, this is not an out of order scoreboard. Okay, you could do out of order execution on a GPU, but it doesn't make any sense. Why do you do out of order execution? Yeah.
For serial parallelization.
Serial parallelization to extract what kind of parallelization?
ISP.
ILP, instruction level parallelism. There is instruction level parallelism in GPUs, right? The code sort of looks the same as CPUs. It's not like you couldn't get something from going out of order. The problem is, well, there's two things. You already have a lot of independent work because you have all these warps. Okay, so you naturally have a bunch of parallelism that you didn't have to pay for, right? When you're trying to extract ILP, you have to pay for that by looking up all the dependencies and keeping track of them and keeping track of hazards and what happened, like what did I issue when? I need a commit buffer to make sure that, you know, things are finishing at different times and they all commit at the same time. So it adds complexity to add all that stuff. And the net win is usually not that big because you usually have enough parallelism in all of the parallel warps. So GPUs will issue instructions in order. Okay, they'll do in order issue. But there's still out of order completion because a load doesn't take the same amount of time as an add, for example, but you will issue things in order from each warp. Okay, so there'll be an in order issue scheduler. So now the issue scheduler's job is to do what? If I know that it has to be in order with respect to each warp, what is the issue scheduler doing? Pick a warp. So now the issue scheduler's decision is not, you know, among instructions in the same warp, it's among warps. Which warp am I going to issue from next? And it uses a scoreboard in the model that we have, at least in simulation, and earlier GPUs used a scoreboard to keep track of these dependencies. Like I mentioned previous in the class, the way that some of these dependencies are handled now is actually inside the instruction itself, right? Remember I showed you those giant, you know, opcodes. So once I decode the instruction inside my I buffer, there's some field that says this instruction needs to wait here for X cycles. And then you basically just make sure that it waits for X cycles, and then then it's eligible for issue. In the simulation infrastructure we use, and like I said earlier, GPUs, there is an in-order scoreboard. In practice, functionally, using the scoreboard and using the encodings inside the instructions sort of will result in the same performance for the most part, as long as you have the latencies correct. It's just an implementation detail. Those SIMT stacks that we talked about in the previous lecture, these live here, okay? And then the issue pipeline needs to know what the active mask is. And the SIMT stack is also feeding the fetch unit to tell it what PC each warp needs to fetch now. Okay, so whatever's at the top of the stack, whatever PC it is, the fetch scheduler will potentially pick one of those warps and issue that PC to the iCache. Question.
Yeah, so the big instructions that we talked about that were encoding dependencies, do they also encode dependencies for structural hazards?
Do they also encode
The scoreboard will prevent structural hazards as well, right?
Well, the structural hazards, the scoreboard doesn't prevent structural because a structural hazard will happen because the pipeline is unavailable.
Yeah.
Right. So it's sort of like the scheduling problem is this: you have work that can be scheduled and you have things that it can be scheduled on.
Yeah.
Dynamically, you'll always know any given cycle whether a particular unit is busy or not. That's something you can tell, and you can pick out structural hazards from the busyness of the unit.
Don't you use a scoreboard to keep track of the busyness, like a fast?
A scoreboard is used for keeping track of the dependencies, right? Now, we do have to worry about write after write hazards, so there is some buffering and ordering that we need to deal with. But structural hazards, because it can't actually know. So think about it. If I have one tensor core on my SM, and I have one warp, I have 7 warps, and one warp issues into the tensor core, the compiler doesn't know that that tensor core is going to be used by this warp when I want to issue this tensor core instruction. So it cannot statically encode those structural hazards because those will happen dynamically based on the concurrency of the workload. It can encode in the instruction stream, like, I know that this ad takes at least 7 cycles, so you have to wait 7 cycles to issue this dependent ad. It can encode that, but it cannot encode the structural hazards that occur from the other warps attempting to use the same structures.
So if we get rid of the scoreboard, how do we deal with the structural hazards?
Well, the structural hazards are easy, right? In some ways, every cycle, you know what units are available. So I check the opcode on the instruction that I'm considering issuing. If the unit that performs that opcode is not available this cycle, then that's not able to issue,
Right.
right? Does that make sense? It's pretty straightforward exercise.
For that, don't you still have to check like a functional unit status table to know what functional units are busy?
Well, you need some kind of way to encode what functional units are busy, yes.
Right, yeah.
But that's a bit vector, right? I mean, can I issue this cycle? Can I not? Can I push it into this pipeline register or not? But yeah, you do need some way to detect structural hazards. And that has to be dynamic because there is this interference among the warps that are happening at the same time. You can't put that in the instruction stream. Good question, though. Other questions so far? Okay, so we've got this sort of front end that's feeding things, then it will issue. So you sort of, hopefully you sort of have an idea of how all of this is working. Again, it's very similar to how a normal or an in-order CPU pipeline would work, except we have this decoupling of the front end and the back end, right? The I buffer. It is, I mean, that also happens in CPUs too with the issue queue. And then once I know that a particular warp can issue, I send it into the read operand stage. Okay, so this operand collector is essentially reading the operands. I haven't told you what an operand collector is yet, but think of this as a register file. It's like a fancy man's register file because register files are hard on GPUs because they're so large and they need a lot of bandwidth. And we'll discuss how they get architected in a subsequent lecture. So after you know it can be issued, you read the operands. There's typically no forwarding in GPU pipelines, so you have to wait for the previous result to be written before you read the dependent value. And then it can go into any number of pipelines. In this simplified data path, I've only shown like an ALU SIMD pipeline and then the memory load store unit. Real GPUs have, modern ones have tensor cores, they have special function units. All of those blocks in that sort of white paper diagram I've showed you before with all those little CUDA cores, all of those are their own independent scheduling pipelines that you can put work on. Okay. Questions on this? Okay. So we call this a 2 scheduler or a 2 loops approximation because you have one fetch scheduler at the front end that's deciding what to send to the iCache, and then you have a second scheduler that decides what to issue when. Okay, and this is more complicated than that first barrel execution pipeline that I showed you, where it was just dead simple because you only ever, if you issued something, if you fetched something from one warp, you waited for that thing to complete before you could do any other instruction. If I don't want to do that and I want to allow each warp to continue issuing instructions while there are warps still in the pipeline, which is highly beneficial, then I need to do this decoupling. Okay, so I have one scheduler to do the fetch and then one scheduler to do the issue. And then this instruction or this scoreboard is going to basically just keep track of dependencies, and we can issue it to multiple SIMD functional units on any given cycle. Okay. Questions? Exciting or boring? This stuff, I like this stuff. Maybe people don't like. Some people like this, some people don't. And we're going to get more into the guts of how this is designed and working. And the simulator that you'll use for the second half of the class models this on a cycle by cycle basis. You have models each of these components, and you run CUDA programs through this thing to simulate the timing. Okay. All right, that's it for today. Last question, go ahead.
Is this scoreboard doing nothing except encoding the dependencies?
Yeah.
Okay.
Yeah. It's just basically saying I'm writing to this register. I'm reading from this register. I need to stall based on the read-write patterns. Okay. Or the write-write patterns if you've got out of order writes. Okay. Okay. All right. You're free. I will see you on Tuesday. For real. Please read the CUDA. I will make a quiz. I swear to you. Oh, I can't swear to you. No, I actually have to do it. I'll do it this weekend. So please read the Gudina paper and we'll have a quiz on it on Tuesday. Okay. All right. Thank you. Have a good weekend.